Hello, good morning, everyone. My name is Sinan Du, and I am in charge of the public outreach in the Department of Physics and Astronomy at UC Riverside. My background is in astronomy. Well, today we are very excited to continue our Cosmic Thursdays lecture series, which has been running for years, but mostly in person. Well, during these special times, we're very glad that we can keep running this kind of event on a virtual platform and also continue to serve our local community. So that's very exciting. And we do appreciate your attendance now and to this talk. We would certainly love to collect your feedback on how we did, either good or bad for this event, so we could improve next time and keep bringing astronomy and science to everyone. Well, today it is my pleasure to introduce our speaker, Professor Simeon Bird. He received his PhD in astronomy from the University of Cambridge, after which he worked as a researcher at Princeton University, Carnegie Mellon University, and Johns Hopkins University with very prestigious research fellowships. He's now a professor in the Department of Physics and Astronomy at UC Riverside, and his research interest is in cosmology, which is the study of the universe on a very large scale. Professor Bird is an expert in dark matter also, and today he will be talking about everything we know and things we don't know about this mysterious substance. Finally, before we officially get started, I'd like to thank our lovely volunteer today, and they are Maddie Queslow.
Hello.
Hey, Garrett Lopez.
Hello, everyone. Hope you enjoy the show tonight.
Awesome. And Nako Gangali.
Hi.
Evan Okolum.
Hello, thanks for coming.
Awesome. They will be moderating the live chat, which you can see on the right-hand side on the YouTube website page. We welcome all kinds of questions and also encourage you to engage in discussions. The volunteers will answer some of the questions and also relate your questions to the speaker as we go along. So without further ado, take it away, Simeon.
All right, thank you very much. So it's a great pleasure to be giving this talk. I hope everyone can see my first slide. It should be working, right? Yep. Okay. All right. So I'm going to give you tell you a little bit about everything we know about dark matter. So the fact that I can fit this into a 45-minute talk should be a clue to you that everything we know about dark matter is not that much, right? So let me begin. So here we have first a picture of dark matter. So I want to emphasize first that this is not a real picture. Right, this is a picture from a simulation, and because it's a simulation, because it's a computer, a model of how the universe works and how the universe has evolved, we're allowed to make it look however we like. Right, so this is a model that's been painted bright colors wherever there is dark matter in the simulation. So the brightest bits of it are the most dense area of the simulation. If this were a real picture, you wouldn't see it like this. If this were a real picture, you just see a black screen. You see absolutely nothing, right? No one wants to look at a black screen. So for this reason, we took our simulation, our computer, and we painted it nicely, okay? But this brings us to the first thing we know about dark matter. The first important fact I'm going to tell you in this talk, it's dark, okay? So the clue is in the name. So dark matter is dark, it doesn't glow. So on the right here, I have a picture of a galaxy of some stars glowing in the universe, and these emit light, and we can see them through our telescopes, right? We can see where the stars are just by collecting photons. Some of them are blue, some of them are orange. We just look for them. Here on the left, I have this computer simulation of dark matter, right? But in the real universe, it doesn't look like that. In the real universe, dark matter is just this invisible thing. It's completely dark. It doesn't emit light at all. Okay. I should mention at this point, I really hope that you will ask any questions that you have on the YouTube. One of the disadvantages of doing this remotely is that when I'm in a room with all of you, I can stare you deep in your eyes, and if you don't understand what I'm saying, I see the expression on your face, right? But because you're not here in front of me, I don't know that, right? So I don't have any idea if if you're not following, or if there's something that's confusing. So I hope that if there is something that's confusing, you'll ask it on the YouTube chat. So okay, so to continue, dark matter is dark, right? It doesn't glow. It's actually more than that. It doesn't interact with normal matter at all. So if there is a large collection of dark matter that is coming towards you, you're not going to see it because it's invisible. It's going to come towards you. It's going to pass straight through your body and go out the other side, right? And nothing's going to happen. You're not even going to notice. It's just going to go straight through you. It doesn't interact. The only thing it does is gravitate. So if there was a sufficiently large amount of it, you would feel its gravitational force, but normally you wouldn't notice, right? So in other words, dark matter is like MC Hammer. You can't touch it. Another great thing about being on YouTube is that if no one's laughing at my bad jokes, I don't notice. So I'm just going to assume that you all laugh there. Yeah? Even though these jokes are kind of old man jokes now, because no one I think who's listening has ever heard of MC Hammer anyway. So dark matter is dark, it doesn't glow, and it doesn't interact with normal matter at all. Okay, so this means that we know something that it isn't, right? It's not atoms or stars, right? The atoms and the stars that kind of glow and form galaxies, this is not what dark matter is. It's something else. It's this mysterious, invisible, non-interacting stuff, right? So this is the great challenge. Okay, good. Some people are laughing in the chat about the MC Hammer joke. That's great. The challenge of dark matter is to work out what it is, even though it's dark and it's not something that we're familiar with, right? So, okay, so first thing is it's dark. What is the second thing we know about dark matter? So maybe you can guess this one, right? So the first thing we know about it was that it was dark, and it's called dark matter. So the other thing we know about it is that it's matter, okay? Hence the name. So dark matter is dark, it's not atoms or stars, and it's matter, right? So what does that mean? So I mean it's not a force, right? Gravity is a force. There are some other things that are force. Electromagnetism is a force. Dark matter is not that. Dark matter is matter. It has mass. It takes up space. There's an area of the universe where there is dark matter, and there's an area where there's more dark matter, and there's an area where there's less dark matter, right? So it's a thing. It's not a thing that you can touch, but it's still something, right? So I keep wanting to say, oh, it's matter, it's tangible. It's not tangible. You can't touch it, right? But it has a space. It has an area associated with it. So it's matter. How do we know this? So we know this because we've done experiments to find it out, right? So okay, so this is a famous picture of the bullet cluster. Again, the first picture I showed you wasn't a real picture, right? The first picture I showed you was a simulation, a thing that came out of the computer. This one is a real picture with artificial colors painted on it, right? So the red and the blue are not the real colors of the image. No one pointed a telescope and saw the red and the blue. The red and the blue have been added in analysis, right? So we've taken this image and we've worked out some features of it, and then NASA has painted the red and the blue on. And the red has been painted where there's gas in the image. So they've seen the gas in a different wavelength, and they've painted onto this image of galaxies, right? And so the gas is mostly hydrogen. It's the stuff that exists everywhere that is between the galaxies. Gas is very important in astronomy. There's a lot of it, a lot of gas everywhere. But the only thing that's more important is dark matter. There's even more dark matter. The blue thing shows where the dark matter is, right? So what we've done here is we've taken the strength of the gravitational force and we've painted on in blue. And what I want you to get from this is that the blue and the red are not in the same place everywhere. So the dark matter has its own space, right? The gas has space and the dark matter has its own space, right? It's like some grumpy father that has his own garage, his own space where he can live in, okay? So this shows that the dark matter is matter, right? It's a thing that exists sometimes separately from where the gas is, all right? So what is this? So dark matter, it's dark, it's not atoms or stars, it's matter, takes up space. Two things we know about it. The third thing we know about it is that it exists, okay? So this is an important thing to know about anything. If I were going to give you a talk about dark matter and then say at the end, oh, by the way, we don't know whether it exists or not, maybe you would be less impressed. You would say, feel a little cheated somehow that, oh, I'm going to tell you about something. Maybe it exists, maybe it's not. That's not what you come to hear here. So it exists. How do we know that it exists? Given that we can't see it and we know that it's not atoms or stars or normal matter, all we know about it is that it takes up space. So the way that we know it exists is that it gravitates, right? And we can measure how much it gravitates, what the gravitational force is that comes from dark matter. So, okay, so let me show you this plot. So this is a famous plot. This is the first solid evidence for the existence of dark matter. What is this? This is the distance from the center of the Milky Way in thousands of light years. And this here is orbital speed. So each of these dots represents a star, right? So all the stars in the galaxy are rotating around a common center. So here's the common center, they're rotating around them. And they all have this orbital speed. So they all move around this common center with some common speed, just about 200 kilometers per second. That's quite fast in terrestrial terms. The galaxy is, however, excessively large, so it takes a long time for them to go around. I think the sun has been around a few times since the formation of the Earth, right? So the galaxy is very large. It takes a long time. It's kind of strange that they're rotating at the same speed, right? Anytime you see something in science that is always the same, you kind of want an explanation for it. Even more strange is that this is the rotation curve for the galaxy, right? So they're moving at a constant orbital speed of about 200 kilometers per second, all the way out, 100,000 light years away from the center. This is the rotation curve for the solar system. So you notice these two curves don't look anything like each other. So that's a little strange, right? This is even more a little strange because the reason that the rotation curve of the planets looks like this is the laws of Kepler. So they were discovered by this guy, Johannes Kepler. Here's a picture of him here. You see he has a great big beard, which signifies that he's a scientist in the 16th century. And he has these instruments here with which he's measuring the angular size of the planets. He comes up with Kepler's laws, which is basically the shape of this curve, right? The way that the orbital speed of the planets drops off as you get further away from the sun. Right, so Mercury is moving very fast. It's very close to the sun. It zips around very quickly. The Earth, of course, takes about a year to get around the sun. Mars takes somewhat longer because it's moving somewhat slower, and so on and so forth, all the way out to Pluto. Right, so all of these planets and Pluto are moving at a reduced speed the further away from the sun they get. Okay. And the realization that was made by people following Kepler was that this was because of gravity, right? So gravity is a universal force, and it attracts all of these things to the center of the solar system in proportion to the distance they are away. So as they get further and further away, the gravitational force of attraction gets weaker and weaker, and so they move slower. All right. So okay, this is why the orbital speed in the solar system drops as they get further away. Gravity is weaker. Fine, but gravity is supposed to be a universal force, right? Everything is supposed to gravitate the same. So it's strange, right, that this curve for the solar system has this wonderful shape. This curve for the galaxy has a completely different shape. Why is that, right? I mean, hopefully gravity is the same. Why is it that, that this thing is like this and this thing is like this, right? Is the force of gravity not dropping off, as quickly as you leave the center of the Milky Way as the solar system? So that's not the case. What happens is that there are different things in the solar system compared to the galaxy, right? So if you look at the solar system, to a very good approximation, the solar system has one thing in it, and that is the sun. This 99.9% of the solar system mass is the sun. It's this giant thing in the middle of the solar system, and everything just rotates around it, right? So, they don't gravitate themselves. They just feel the pull of gravity on the sun. I'm sorry, they gravitate themselves a very little bit, much less than the force of gravity on them from the sun. And this is what controls this rotation speed. So as they get further away from the sun, its gravitational influence weakens, and so they move slower. Okay, so what the rotation curve of the galaxy is showing you is that the galaxy is not like the solar system. So in the solar system, all of the mass is right in the middle, right at zero distance from the center. In the galaxy, the mass is spread out. Okay, so to explain this curve, what you need is you need a whole bunch of mass outside each curve. So the sun is sitting kind of here at this black dot. And inside the radius of the sun, there's a certain amount of mass, and then outside the radius of the sun, there's a bunch more mass, right? So the mass of the galaxy is spread all the way around the rotation, this radius of 100,000 light years, and actually a little bit further. Okay, this is fine. You know, sure, you say, I've seen a picture of the galaxy. In fact, there's a picture of the galaxy right here on your slide, Simeon. You know, the galaxy is a giant disk, right? It doesn't have a single object in the middle and then a bunch of other faint objects. It's this giant disk of stars. So why is this evidence for dark matter? You know, clearly there is mass outside on the outskirts of this galactic disk. Well, the answer is that you can count up the stars, right? You can count up all the things that are glowing in this picture, in the background here. You know, and you notice that you know, that even these are a little bit concentrated towards the center. You know, the outskirts are slightly dimmer than the interior. If you count up the mass of all these stars and add them all together, it comes to much, much less. You know, maybe a factor of 10 or 100 less than the mass that is required to explain this rotation curve. Right? So even with all these stars outside, there's still not enough. There has to be a whole bunch of matter that's in the galaxy that isn't producing light. What is that matter? Dark matter, right? This is something we can't see, it's not producing light, so we call it dark matter. Okay? So I hope that makes sense, and feel free to jump in. This is the original evidence for dark matter. It comes from Vera Rubin. You know, that's why she has a telescope named after her now. I'm going to talk about some other evidence now. So this, oh, I'm sorry. Before I do that, I should mention that this isn't just our galaxy, right? So every galaxy that we observe, every galaxy in the whole universe does this, right? So this tells you that dark matter is not just a strange thing connected with our galaxy. It's something that that happens in every galaxy in the universe. It's absolutely everywhere. All right, so this is a universal thing. Right? Different amounts of dark matter in different places, but universal dark matter. Okay, so some more evidence for dark matter, which doesn't get talked about as much because it wasn't the first evidence, but it's very good evidence, and it's very difficult to argue with evidence, comes from the early universe, right? So at the beginning of the universe, you know, the universe was much hotter, it was much denser, and there was this thing called the Big Bang, where the universe was hot, dense, all crammed together in one place. And as it expanded, it cooled down, and there was a burst of light that came at a particular point in the early universe. Right, so this light, it was originally emitted as sort of, you know, very hot. Since then, it's cooled down, and now it comes to us as a sort of bath of microwave photons, right? So if you switch on, well, okay, this is not true anymore. If you're very old, you remember the time when you switched on, such as I am, when you switched on an analog television and there was snow, right? And you just saw just kind of noise in the picture. About half of that is microwave photons that come from the very early universe. Right? So every time you switched on your television, you saw the beginning of time. Yeah. So this early light, we've measured it for many years very precisely, and because the early universe was very hot, you know, we understand pretty well how it comes about, right? So we understand how it works, and we know that of all the things emitting light, you know, we know what emitted light, and we know how much stuff there was, right? And so we know that these two numbers don't match up. Right, all the stuff that was emitting light, you know, we see the amount of light, we see how it's distributed. This is the map of the light that we see in the universe. That the whole sky looks like this, and we know that there was a lot of stuff in there at that time that did not emit light. So this is what the dark matter is, right? So this tells you that not only is dark matter everywhere in space, but it's everywhere in time as well, right? So it's in every single galaxy, and it's from the beginning of the universe to the present day, right? So dark matter really is this universal thing. Okay. Yes, okay, so what do we know about dark matter? Firstly, we know it's dark. Good thing to know. Secondly, we know it's matter, takes up space. And the third thing we know is that it exists. Right, so far what I've told you, you could have figured out from the title. You didn't need to come to my talk to know this. I'm going to tell you a little bit more now. So not only does it exists everywhere, and there's a lot of it. So sorry, one more thing before I go into that. You often see people when they talk about dark matter make the name a little bit longer. So it's not just dark matter, but it's cold dark matter. So what does that mean, right? So this is more complicated. What does that mean? Let me show you a picture of a warm thing. So this is a warm thing. This is an ocean somewhere in the tropical Pacific, right? This ocean is warm, it's flat, it looks wonderful. You'd love to go swimming in it. One property of this ocean is that if you're swimming in this ocean, swimming like this, and you stand there, tread water for a little bit, and you try and pick up some of the water in your hands, try and kind of gather it up into a tower of some kind, then you let it go. It's not going to stay there, right? You pick up water in your hands, you let it go, it's just going to splash out and go back to being a flat ocean, right? So there's no way you can gather this water together and have it stay there after you've gathered it together. Okay? And this is because it's warm. Okay, so let me now show you a picture of a cold thing. This is a cold thing. This is a frozen lake. So I'm guessing that, okay, this serves multiple purposes, right? Firstly, this is a pedagogical example of a cold thing. Second, this is a thing to take your mind off of how unreasonably hot it is right now, and how your air conditioning maybe isn't working as well as it is because you're trying, as well as it should, because you're trying to save energy and help the state avoid blackouts. Right, so this is a picture of a cold thing. Right, this is a frozen lake. You don't see these very often in Southern California, but if you go to the upper Midwest, you'll see that the Great Lakes in winter, they all freeze over completely. And when they freeze over, they look like this. They don't look smooth and flat like an ocean. There's piles of ice rubble everywhere, right? All these broken sheets of ice that have cracked, refrozen in slightly different shapes. Someone's kind of hammered them. Someone's trying to make a road in the middle and piled things out outside it. More snow has fallen. There's stuff there, right? There's huge mountains, there's structure. And this happens because ice is cold, right? So the molecules in the ice bond together. They form crystals, and the crystals grow into chunks. They form bricks, and then the bricks kind of collide together in these great structures, right? So that's what it means for something to be cold. It's something where if you put it together, it sticks. A warm thing, the molecules in the water, they're really warm, and they zip back and forth, and you can't hold them together. They escape very quickly. The molecules in the cold ice stick together sufficiently well that they just stay together. Okay, so let me reiterate that. A cold thing is something that you can pile up. So I say gravity wins. In the case of ice, it's not gravity. Well, I guess it's the Earth's gravity, but it's the molecular bonds that holds the ice together. Something keeps them together. If you pile it up, it stays there. In a hot thing, the thermal energy is so strong that the thermal energy pushes everything apart. The hot things don't pile up, they just kind of spread out everywhere. Okay, so for a cold thing, gravity wins. For a hot thing, thermal energy wins and things just smooth out. All right? So dark matter is like this. So when we say cold dark matter, we mean that it's like the ice. It piles up, the gravity can win. So here is a picture. This is again a computer picture, right? This is not a real picture. On the left, I have a computer picture of cold dark matter. And on the right, I have a computer picture of hot dark matter. So on the left here, I have, it looks like a giant has been spraying a paintbrush at the page, right? There's all these kind of splatters and lines, all this kind of stuff kind of messed around in the middle, right? On the right, for the hot dark matter, it's smoothed out, right? I see a few blobs of lines in the middle, but mostly I see this smooth cloud just everywhere. And if you look at a zoom in, I've zoomed in to a part of the upstairs picture down here, you can see that there's these big galaxies in the middle, and then there are lots of tiny little galaxies, tiny little blobs. Each blob contains a little galaxy all the way around it, right? So all these little blobs are kind of scattered around, and there are lots of them. If I look on the right-hand side, there are far fewer blobs, and the ones that are there are much smoother. They're much less knobbly. There's less clumps, right? So that's what we mean when we talk about cold dark matter. Cold dark matter is dark matter that forms clumps, and hot dark matter is matter where the heat of it smooths everything out, okay? And we can measure the fact that there isn't this smoothing effect. Actually, the best constraints on this smoothing effect come from measuring intergalactic gas, and they're done right here at UCR, right? So this is this is how we know. This is UCR's, contribution to international science, or one of the contributions to international science. Right. So okay. So what do we know about dark matter? Just to reiterate, it's cold. It's hot. Sorry, it's cold. It's dark, and it's matter, and it exists. Right. So the clue is in the name again. Cold dark matter. It's cold. It forms clumps, and ultimately it forms galaxies, even small galaxies. It's dark, so it's not atoms or stars. It's just a thing that doesn't emit light. And remember, if it comes towards you, it'll just pass straight through you, right? It's not going to interact with you in any way. It's matter, so it's got its own space, and we know it exists, and we know there's a lot of it. We know it's everywhere in time and everywhere in space. Okay, so okay, I said there's a lot of it. How much of it is there? Okay, so this is a pie chart telling you how much dark matter there is. So if you look at the amount of stuff in the universe, the 100% of the stuff in the universe, 5% of this stuff is in atoms, is in the normal stars and planets and gas that we know and love. Actually, most of it is intergalactic hydrogen, but so the amount that's in stars is even less. 27% of it, so 6 times more than the atoms, is in dark matter. The rest, 68% of it, is in dark energy. So the stuff that we know of the universe is actually a very small fraction of the total amount of stuff that's in it. The atoms that we know, the stars and the gas, is maybe 5% of the total, and 6 times that is in dark matter. So okay, so I've now told you everything we know about dark matter. Let me tell you instead. Is the YouTube still working? I've gone back to my first slide on YouTube. Is that okay?
Oh, no, we're still good.
Okay, we're still good. I'm sorry, it was just my link then. Okay, so before I go on to tell you some things that we speculate about dark matter, let me tell you a few things that about dark energy, right? So let me just give you a quick comparison between dark matter and dark energy, the different things, right? So firstly, the things that are the same between dark matter and dark energy. So they both exist, which is good, because it would be, it would be strange if I were giving this talk about dark energy if it didn't exist. I'm sorry, I should really say, as far as we know, to the best of our belief, they exist. We have good evidence that they exist. As a scientist, I shouldn't be saying they definitely exist, because this is recorded and it's going to be on YouTube. And if I say they definitely, absolutely exist, and then in 100 years' time, someone comes up with some great idea that we've all missed, and there's some other explanation, I'm going to look really kind of silly. To the best of our knowledge, given our very good evidence, they exist, right? And they're different things. Dark matter exists, and there's 6 times as much dark matter as there's normal matter. Dark energy exists, and there's 3 times as much dark energy as there is dark matter. Dark matter is dark, just like dark energy. They're both dark. Neither of them glow. Neither of them are luminous. So these are 2 points of similarity. 2 differences. Dark matter is matter, like I said. Dark energy is not matter. Dark energy is a property of space somehow. It's a thing that just is made up of space. For some mysterious reason, hence why it doesn't have a better name than just dark energy. Dark matter is cold. Dark energy is not cold. So dark matter forms clumps and structures, and there's different amounts of dark matter in different places. Dark energy has the same density everywhere. Okay. So that's a comparison between the two. Let me move on now. So I've now told you everything that we know about dark matter, cold dark matter. Let me tell you what we don't know about cold dark matter. So the major question we have about cold dark matter is a very simple one. What is it? Right. So we know it's this stuff that forms gravity, that causes gravity. It causes a lot of gravity. There's a lot of it around. But what is it actually? Does it do anything else? So we don't know the answer to this question. And I would say that we emphatically don't know the answer to this question. We thought we have some ideas. At the moment, all of the ideas that we have some problems associated with them. And I'm going to talk about a couple of the most popular ideas. They are popular today, right? Everything I've told you now, the next time someone gives a talk, it might be different. Okay, so just to warn you. So one popular candidate, and this until recently, this was extremely popular, is that dark matter could be a particle kind of like a neutrino, but much colder. So what is a neutrino? So neutrino is Italian and it means little neutral particle. It's called that because when they discovered it, they had a bigger neutral particle already, which is called the neutron. They are little particles, they exist, they're dark in the sense that they don't emit light. And when a neutrino passes through you, actually, many millions of neutrinos are passing through you from the sun every second. You don't feel it, it just goes straight through, and they're matter. There's one problem with this. Maybe you can guess what it is. I told you they exist, they're dark and they're matter, but they're not cold, they're hot. Right, so neutrinos are hot dark matter, so they can't be cold dark matter. They're not a good dark matter candidate. As an aside, there are no good images of neutrinos because they're fundamental particles and they're dark, so they don't make good pictures. So I've put here an image from the movie 2012, which has as a plot line that the neutrinos from the sun start mutating. Because they're hot dark matter, they heat up the Earth's core and destroy the Earth. And it's all very exciting and a very entertaining movie. I want to mention here that it's kind of silly of me to make fun of such a movie that is clearly not meant to be a realistic depiction of anything. But just to be pedantic, although the neutrinos that come from the sun are very hot, and they can't mutate to heat up the Earth's core, but even if they could, although they're very hot, the Earth's core is actually just as hot as those neutrinos. So if they did mutate, they wouldn't really do anything very much. They would just kind of sit around in the Earth, not making things hotter or cooler, but just kind of going through it. So the movie will be very different and probably much duller, which is why I don't get invited to write movie scripts very often. Anyway, okay, so neutrinos are not a good dark matter candidate because they're hot. We as physicists like to reuse concepts. So if we have a concept that almost works, we're going to take it and we're going to modify it so that it does work, right? So if we take a neutrino-like particle, a neutrino that it could be dark matter except it's too hot, we'll say, okay, what if there's a thing that's very similar to a neutrino, except it's cold, okay? So we're going to take the one thing we don't like and we're going to make a thing that's very similar, but with that thing removed, okay? So people did this, why not? This turns out to be a great idea, okay? And I mean this in the sense of it's a wonderful idea. Whoever had this idea, I know who had this idea, he's very happy, okay? It turns out to work really, really well, okay? In theory. You work out the numbers for this, and you work out whether it explains how much dark matter there is, and it does. And you work out what temperature it should have, and it's really cold. And you work out how dark it should be, and it should be really dark. It explains all the known facts of dark matter really, really well. And not only that, it suggests very good experiments to find out what this thing is. Okay, so you can look at the way this thing interacts with other standard model particles, other particle theory particles, and you can do an experiment to test that. Okay, kind of similar to the experiments you do to find neutrinos, but much more sensitive. So this is wonderful. This is everything a scientist could imagine, right? It has a wonderful theory that makes solid predictions and explains the evidence parsimoniously, and it suggests experiments that we can build and do and measure it conclusively. It's testable. The only problem with a testable theory is what happens when it doesn't pass the tests, right? So 10 years ago when I was a grad student, everyone thought this was true, right? We're going to build the experiments, and in 5 years' time was going to detect it. Now, we're kind of getting worried, right? So this is a plot. Don't pay any attention to the axes, just say that this is a plot and the neutrino-like particle sits somewhere in the middle of this plot, okay? The gray area was ruled out in 2012. We've now reached the blue line and that area is kind of ruled out. So there's an increasingly narrow range for these things to sit, right? So, 10 years ago we said, oh, we'll find it in 5 years. And now it's been 10 years and we haven't found it, right? So we're kind of getting to the point where like, well, we should have found this by now, this is kind of, this is getting uncomfortable. And I don't want to say that it's not there, right? There's still this extra range kind of down here, this area between the red curve and the blue curve where it could be. But maybe tomorrow this talk is going to be obsolete as someone announces, has a big press conference, we found this neutrino-like particle, the problem of dark matter is solved, right? But I'm not holding my breath, right? Because the theory numbers kind of expect it to be up here somewhere, to be completely honest with you. So this is kind of worrying, right? This was a very popular model. It made strong predictions, and the predictions have not been confirmed. So we're worried about it, right? So this, it's still there, and I'm going to show you the other models have other problems, but it's looking dicey, right? This is why we say the end of the road, right? It's not that we've reached the end of the road, but we're facing it. There's a sign and it says no outlet. Okay, so let's look at other models. What other things do we have? So other possibilities, okay, so we have a heavier neutrino. Another possibility we might have is black holes. Okay, so black holes. Why could black holes be dark matter? Well, okay, so properties of black holes. This is a picture of two black holes from the LIGO collaboration. These are these black disks right in the middle here. And they're going to circle each other. So what do we know about black holes? So black holes actually are very cold. They're dark in the sense that they don't glow very much. It's not true that if one comes towards you, you wouldn't feel it. If a black hole comes towards you, you notice, and it really hurts. But you can get around that because the black holes are sufficiently rare that one doesn't come towards you very often. As long as nothing falls into them, they're dark. If something falls into them, they glow. But if nothing falls into them, they're dark, and they're matter. Right, so okay, black holes, they're cold, they're dark, they're matter. So that makes them a reasonably good cold dark matter candidate. So could they be the dark matter? Well, okay, so there is a problem with this too. And that comes, I told you that there are 4 things we know about dark matter, and I've only listed 3 of them here, right? So the fourth one is that they exist and that there are enough of them to explain the dark matter. And that's the problem with black holes as dark matter. So most black holes in the universe form when a massive star explodes. So you get a massive star, it explodes, the core of it contracts and becomes a black hole. This does not work as an explanation of dark matter. Why not? Because I told you, remember, that there is 6 times as much dark matter as there is atoms, which means there's a lot more dark matter than there are stars. So even if all the stars in the universe turn into black holes, there still will be nowhere near enough dark matter. Even more, I told you that there's dark matter today and at the beginning of the universe, right? So the dark matter was there before there was a chance to form stars. So, you can't have, unless it's somehow the stars formed first in the first microsecond after the Big Bang, immediately exploded and became a black hole. That doesn't really make sense, right? So the dark matter can't be, the black holes from exploding stars can't be the dark matter because there just aren't enough of them, right? So they're cold, they're dark, they're matter, but they don't exist enough. There isn't enough of them. This is a problem for this explanation. There is a solution to this problem. And this is a very wonderful and very physics solution. The solution is, let's say they're not collapsed stars. Just like with the neutrino, I said, okay, the neutrino could be dark matter, but it's got one fatal problem. The black holes could be the dark matter, but they've got one fatal problem. And the fatal problem is there aren't enough of them. The solution is, okay, let's create a new type of black hole that doesn't come from stars. Where does this black hole come from? It doesn't come from anything. It's just there at the beginning. So right at the beginning of the universe, just at the very first sub-microseconds of the Big Bang, you just get dense objects that just spontaneously collapse and form black holes. So the wonderful thing about this explanation is that at the beginning of the universe and the Big Bang, everything's so hot and dense that there's nothing we can do to probe it, and to some extent there are no rules. So you can do whatever you want to do. And if what you want to do is to create dark matter, you create a rule that creates dark matter, and you say, okay, this rule is needed, right? So at the beginning of the universe, we create a whole bunch of black holes, just enough to explain the dark matter, and then we keep them going to the present day. If you're saying that this is a very slightly contrived solution, you would be right. However, this explanation of black holes is an old one. And it's a good one to think about. And recently, it also makes testable predictions. And recently, it got a big boost. And the reason it got a big boost was that you may have heard that the LIGO experiment detected this gravitational wave signal from two black holes colliding with each other. Right? So because these two black holes collide each other, and because it sees so many black holes colliding with each other, and these are the numbers down here at the bottom of this screen of the number of black holes that are colliding with each other every year in every region of space around us. There are more black holes of this mass of about a few, maybe 10 times the mass of the sun, more black holes than we really kind of expected to be there. So this kind of gives a slight boost to the idea that maybe, since there are more black holes than we thought there are, maybe some of these, are not from stars, maybe they are the dark matter, right? So yeah, this is an interesting idea. I wrote a paper about that. I had a lot of fun writing the paper. I had this number 2, which was kind of in the right range, so that the numbers kind of worked out. There is, unfortunately, yet another problem, which is that, again, we should have detected them, right? So all these theories have these great predictions. People go out and look for them, and they don't find them, right? So this is why dark matter remains a mystery, okay? So this is a plot. I like to show you these plots of the limits on the fraction of dark matter. This one here. So up here we have all of the dark matter in black holes. This is 1/10 of the dark matter in black holes. This is 1/100th of the dark matter in black holes. As a function of possible black hole mass, and the black holes that have been seen merging are around here. And you can see that, we've done an experiment that means that less than 10% of the dark matter can be these black holes. So that's a shame. That doesn't, this means that the black holes can't explain all of the dark matter. If you're paying really close attention, you'll notice that there's this region here for black holes with a mass of around the moon or an asteroid. So this is about the mass of the moon. This is about the mass of the asteroid. And you'll notice that these aren't ruled out by anything. So that's a very good point. That is a plausible model for dark matter, and one that we should do a lot to try and detect in the coming years. So let me sum up at the end these things that we don't know about dark matter. So what is the dark matter? So I've shown you a couple of possibilities. The popular ones are a colder particle that's kind of like neutrinos, but just colder. A second one is that it could be black holes, very massive black holes, which somehow there are more of them than there should be. I've put in option 3, a variety of weird particles. I apologize to my colleagues who worked on these weird particles. They're not really weird. Each of them is special in their own particular way. Each of them has their own really good reasons for being the dark matter candidate. I just don't have time to go into them. It could very well be one of these things. And then option 4, I want to put that here because, all of the above. Maybe dark matter isn't any one single thing. Maybe it's a whole bunch of things, right? The real world, the light world that we see is full of different kinds of things. It's full of hydrogen, helium, stars, planets, a whole bunch of stuff. Maybe the reason we're having such difficulty detecting these dark matters, these different dark matter candidates, is that each of them only makes up, 10% of the dark matter, and there are 10 different types of dark matter. Okay, in one sense, this would be terrible because it means it would be very difficult to detect anything. In another sense, it will be great because it would provide lots of fun problems for physicists to think about for the next 100 years, full employment. Yeah? I kind of, if I'm honest, in my personal opinion, I incline towards the last one. And the reason for that is just that reality is always messy, right? Anytime you think you have a simple model for the universe or for how something works, the reality turns out to be much deeper, wider, and more wonderful than you thought it was. So I'm going for all of the above. And just to give you, once again, so you don't, you feel that I told you what I promised to tell you at the beginning. All the things we know about dark matter, again, it's cold, so it forms clumps and galaxies. It's dark, so it's not atoms or stars. It's matter, so it takes up space. It needs its own space, and it exists in 6 times the rate of normal matter, and we don't know what it is. So that's my talk. This is exactly 45 minutes. Thank you very much for listening. I hope you enjoyed it. Please let me know any questions that you might have. I think Shinan has been collecting them.
Yes, great. Thank you, Simeon. Yeah, well, before we go through the questions, we will have about 10 minutes. If you have any final questions, put it into the chat and we will answer them as the time permits. But as for now, we have a few questions now already in the pile. So first, Equal asked, I hope Professor Bird will discuss the differences between the cold dark matter model and the self-interacting dark matter model. So that's a sort of like a,
That's a request. It's a feature request.
Yes,
yeah.
And I know it's a little bit technical. So,
do you want me to answer it anyway?
Yeah.
Yeah, let's make this guy. Let's make this person happy. This is what we do. So I told you that dark matter, doesn't interact with real matter, with light, with atoms or stars, right? I didn't tell you that dark matter doesn't interact with itself. So maybe if two dark matter particles, bash together, then something happens and it forms a new type of dark matter, and that's called self-interacting dark matter. So the self-interaction is a way that it can do things other than just gravitate, but it only does it, with other things of its same type. It's like it's the opposite of magnets, right? Magnets, a positive charge and negative charge attract. Dark matter is just the same type of dark matter will interact with itself. Of course, the ultimate self-interacting dark matter is black holes, right? When two black holes collide with each other, they interact very strongly and you get a more massive black hole. Okay, so.
Great, thank you. And the next question is from Josh2122. I thought the current model is that dark energy density remains constant even with expansion. Doesn't this mean energy is not conserved?
That's a great question. The answer is both yes and no. Which my favorite questions have the answers yes and no. So that's true that energy, in a sense, energy is not conserved. In practice, you can't do anything about it. There is a technical term, which is the weak energy condition and the strong energy condition. The weak energy condition is energy conserved? And it's that condition that dark energy violates. The strong energy condition is, can you do anything useful with the energy that is created? And for dark energy, the answer is really no, right? So if you had the traditional way to get work out of something, out of a force, is to have you sitting here on one end of a string and someone else pulling on you, right? And then they're pulling on you at the other end, and you have like a little electric motor with a string on. And as they pull, the string comes off off your little motor, it spins the motor, and it generates an electric current. You can't do that with dark energy, because if you sit yourself on the string, and the other person on the other end of a string, you just sit there. The forces between the string is always stronger than the force of dark energy, right? Because the dark energy density is constant in time and space, you just kind of sit here and you are bound together and the rest of the universe expands around you, right? So you can't do anything useful with the energy that is not conserved. So, that's how we get away with that.
Great, thank you. And our next question is from Extra Rush 909. We can detect neutrinos, right? So would we be able to detect a dark matter if it were a heavy neutrino?
Yes. So this is the basis of, that's a great question. This is the basis of this plot, right? So this plot is done by building these tanks full of very inert noble gases like xenon. The experiment here is xenon 1 ton because it has 1 ton of xenon. And you build this tank and you watch for a cold heavy neutrino to zip through it. And if it does, then you'll see a little flash of light. So this is very similar to the way neutrino detectors work. Neutrino detectors, the first one is the first one that detects neutrino is a giant tank of water in Japan with a whole bunch of photomultiplier tubes on the outside. By the way, the photomultiplier tubes are changed by undergrads who have a little boat and go around and screw in 10,000 bulbs by hand. And there's another experiment like that in Canada. So these these are very similar experiments. So the answer is absolutely yes.
Great, thank you. Moving on, we have MM asking, if it was black hole, wouldn't there still be accretion? In that case, wouldn't mean that we're able to detect it as dark matter, maybe?
So that is also a great question. Let me get my light balance right. That is also a great question. The answer is no, because they're primordial black holes. So because they form so early on, when they form, the universe is so hot that they aren't able to hold on to any gas around them. And they're formed with very high velocities. So they're not able to hold on to a gas disk. So normal black holes have gas disks because they're exploded stars, right? So the star explodes, and then each star has a gas disk around it from the explosion and from what was there before. And that gas disk forms the seed of the accretion that the black hole has. The black holes that start off at the early universe, they don't come from an exploded star, right? So there's nothing to seed the accretion disk. So they're bare. They just zip around. They don't accrete very much, so we wouldn't see them. But that's an excellent question, because you might think that we would.
Great, thank you, Simeon. And hopefully that also answered Darren's question. And if not, feel free to elaborate on your question a little bit further, Darren. And next we have Ian asking, thanks for the fun talk. How much space does dark matter take up? What is the relative scale?
It's a lot of space. Yeah. So dark matter, the galaxy is perhaps 600,000 light years across. Did I get that right? Did I get the conversions right? I think so. It's about 200 kiloparsecs across, which is about 600,000 light years. This is large. I'm sorry, I'm getting this wrong. The dark matter in the galaxy is about 600,000 light years across, right? The stars in the galaxy, the sun is, I think, about 1 kiloparsec from the center of the Milky Way. Is that right? I always get this wrong. It's either 8. Yeah, it's either 1 or 10. It's 10. It's about 8 kiloparsecs from the center of the Milky Way. So it's about 8,000 times 3. It's about 24,000 light years from the center of the Milky Way. So the galactic disk of the stellar disk of the Milky Way is maybe 50,000 light years across. The dark matter component of the Milky Way is a factor of 10 larger than that. Right, and the dark matter extends out even further. Although it's not in the Milky Way, there's dark matter everywhere, right? It extends out across millions of light years. So the dark matter is everywhere and is much, much bigger than the galaxies. It's big.
Very big. Great. And next question is from Missile. Are there any current computer simulation research related to dark matter? Wow.
Yes,
Simeon,
there is a lot. If it would be a whole extra talk for me to tell you all about that. Yeah, I mean, that's a lot of what we do, right? We run simulations of how dark matter behaves and how it grows. That's where, let me go back all the way. Yeah, that's where this plot comes from. This plot, these all come from computer simulations, and making these computer simulations more accurate and modeling different types of dark matter, that is an ongoing topic of research. And oddly enough, one of the hardest things to put into a computer is the black hole, because you have to include what happens when they get close to each other, and that's kind of a mess. So.
Great, thank you. And Sandra asks, what does Professor Bird think about the movie Interstellar, about the black hole?
Oh yeah, no, I like that movie actually. I mean, I like that movie. I really like the bit where there's a bit where they're falling into the black hole, and you see the disk of the black hole, projected around it. I love that image because it's a real scientific image of what a black hole would look like if you were falling into it. In this image, the disk that is behind it, it appears above and below because of the way the light is bent around it. So I think that's great. I think the bit where they're on the planet and then 10,000 years have gone by, off the planet, that's really cute too. I mean, I feel like they should have expected that to happen. The bit at the end where like, what is it? Love is the only thing that escapes the black hole. Yeah, that I'm not too sure about. Like the power of love to conquer gravity. Love can do a lot. Gravity, kind of stronger. But apart from that, I love that movie.
Great, thank you. And Rami asked, if we were able to understand everything about dark matter, what implications would that have on our understanding of the current universe and other theories? Would it change our views on anything?
Oh, hi Rami, by the way. I know you're the guy that has worked with one of my students. That is a good question. I don't want to answer that question because the answer depends on what it is, right? So, you know, normally when we answer these kinds of questions in physics, more things fall out, right? So an example of this is, you know, in the 1900s, they were worried about why it was that sometimes light was spontaneously emitted from for the photoelectric effect. Sometimes light is spontaneously emitted under some circumstances. And everyone thought that this was, you know, not a big deal, you know, that it would be explained somehow. It was just a weird quirk. But when it was explained, you know, it led to quantum theory, which it underpins, you know, all the computers that we see today, right? So it turned out to be a very big deal, right? So it depending on what dark matter is, it could have a lot of impact or not a lot of impact, right? So I'm now going to tell you an example of something that I think is really very cute. I think it's probably not going to happen, but it would be cool. So imagine that dark matter were black holes, right? Imagine that the black holes are, as I said in this slide, about the mass of you know, an asteroid or the moon. If you work it out, that it turns out that there's about 1 or 2 of these within the solar system. So I have this sort of, you know, wish fulfillment dream that we discover that this is what black holes are. We discover that there's one in the solar system. We go out and find it. We move it close to the Earth, and we use it for free energy. We dump nuclear waste into it and collect the energy that comes out when that happens. We use it to dispose of all our trash and get free stuff out. This is so that obviously would make a great big difference to everything in daily life if dark matter happened to be that, right? You know, if dark matter were a colder neutrino, this might make somewhat less difference, I would say. I'm not sure, you know, but maybe we discover something useful about it that would lead us to build something else that's useful, or lead us to build a faster computer or something. You never know, right? So the answer to that is, I have no idea, but I look forward to finding out.
Wow, that is a really great answer, especially for the last sentence.
Thank you.
And Darren asks, if black holes compose some, if not all, of dark matter, wouldn't we see a lot more mergers, or would they be large and far apart?
That is a very good question. So the calculation I did suggests that we would see about the same number of mergers as I predicted. And the reason for this is just that the black holes are moving very fast, right? So in order to, you know, if you have 2 things that are moving very quickly, they just pass straight by each other, right? In order to merge, they have to pass slow enough that they can capture each other and spiral around and collide. So probably not. Some other people, in fairness, some other people have done other calculations that suggest that I have underestimated the merger rate, and that you know, there would be more mergers than we see. I personally like my calculation, but you know, these are different assumptions that you can do, and you get slightly different answers, and probably the right answer is somewhere in the middle. So the answer to your question is perhaps no, but it's an ongoing topic of research.
Great, and one last question before we conclude today's talk. The Art of Ramos asks, so there's so much distance in space between things. that these primordial black holes never come across anything since the beginning to attend any accretion disk seems too wild.
Yep, that is absolutely correct, and it is too wild.
Great, thanks for confirming, Simeon. Well, I guess that pretty much concludes our lecture today. I hope you all had a great time and learned something fun about dark matter and the fact that we don't really know a lot of things about them yet. Well, thank you everyone for joining us again tonight. We would really appreciate your feedback on how we did tonight, both on the talk and on event management. So I'll be sending out an evaluation form to you in a couple days. And if you could kindly fill that out for you, for us, that would be great. And everything will remain anonymous. And we're basically just using that for our program evaluation and also to improve our program over the time. So I guess, yeah, that's just 1 minute over. That's it. Well, thank you everyone for attending. Have a good night.
Good night.